Today we are learning about magnetism. I know you're excited. So let's start off with what it is and what it's all about. So we're going to look at the magnetic fields today, forces on these charges, and talking about the right-hand rule, and talking about magnitudes and directions. So first of all, magnets, and what are they? You have a north and you have a south pole. Opposites attract, of course. Likes repel. That sounds like the electric thing almost. And we're going to use magnetic field in terms of B. We use electric field in terms of E. We're going to use magnetic field in terms of B today. And every day we talk about magnetic fields. And the unit for this is Tesla. Okay? So for electric fields, we had a Newton per coulomb or volts per meter, but we didn't have a special unit just for the field. We have a special unit for magnetism, the strength of the field anyway, and that's in Tesla, capital T. Okay? So it's kind of like an electric field. To both field forces, there are vectors. But in the case of magnetic fields, there's no positive and negative, but there's a north and a south. And we defined as the field is pointing from north to the south. So there's an example. There's a north and there's a south here. Now, had we been in class, we could have had these magnets we could pull apart and put them together and everything. And we're going to find we'd be able to examine the fields even in between there. I did put on a couple of places. You can go on the FET. Has a couple good ones. You can use a bar magnet, use an electromagnet. You could also put the earth in. And you might be wondering, hey, there's a north pole and the south pole, so I have two poles. What happens if I chop it in half? If I chop it in half, now do I have a monopole, a south pole, and a north pole? No. Because what you'd find out is you can make the same bar magnet out of a whole bunch of little magnets. And the field goes from, this would be an example of iron filings lining up in the field. The fields have a direction that we call north to south, this direction. Turns out the fields, when you look at that FET, they actually point towards the north on the inside. So when we talk about bar magnets and electromagnets, it's the field points from the north to the south on the outside of it. But within a coil of wire, even though this is the north and south side of a coil of wire, electromagnet, which we'll talk about later, on the inside it actually points the opposite direction. Okay? So what happens is if I were to chop this in half, well, there's a south pole, now I have a new north pole. There's a north pole, now I have a new south pole over here. So I still have little poles. If I chop this smaller and smaller and smaller, the right side is south, the left side is still going to be north. So I really can't cut a bar magnet into separate poles, and you can't have a monopole for magnetism. People have tried to figure out for centuries how would you make a monopole for magnetic fields? You can't. No matter how small you chop this, you can't make a monopole. So there's an example of a larger picture of north to south. On the outside, they point to the south. But the critical part is there's stuff on the inside, and it does point towards the north on the inside of this magnet. All right, there's your magnetic field lines. There's your arrows. Give direction. On the outside of the magnet points from north to south. Okay? And of course, the higher the density of lines, the greater the strength. You go further away, there's less density of field lines. There's less flux. That means there's a smaller field as you move further away, just like you have in electric fields. All righty. So it looks like a dipole because it is. The Earth, it turns out, is a dipole as well. You got a north pole and a south pole. Then look at the lines on the outside of our big magnet, the Earth. They point towards which pole? Pop quiz. Which pole do the lines point to? It's the south pole. Our north pole is actually a south pole. We call it the north pole because if you were to put a magnet, float a magnet, or hanging by a piece of wire, the north pole of the magnet would point towards this, and that's why we call it the north pole, even though it's magnetically, it's actually a south pole. So we're going to find out this field is pretty important to protecting us because we have all kinds of cosmic charged particles flying at this field, and we're going to look at in a little bit how this field helps protect us from this and more about that field and how it could change over time. Okay. So here's the thing about magnetic charges, or to make a magnetic field. There aren't any things called a magnetic charge. There's a north and a south pole always, and they always go together. You're always going to have a north and a south. But the reason they're there is because of a moving charge. When we have our meeting on Thursday morning, we're going to look at the field around a piece of wire. But what we're learning today is really, the only way you can have a magnetic field is you have to have a moving charge. If there's no moving charge, there's an electric field, but there's no magnetic one. So the only way to have a magnetic field is a charge absolutely has to move. Okay? So how do you have a moving charge and a bar magnet is actually a pretty good question. And where is the charge moving and so on. Because as we look back at that bar magnet, I don't remember seeing how a charge is moving anywhere. Well, where the charge is moving is actually within every single atom. So what happens is these electrons, they're not necessarily in orbit about the nucleus. We don't know what they're doing. We know they're moving, but exactly how fast and where they are is kind of another question with the uncertainty principle. But they're doing something. And we have this other quality we like to talk about these charges as in terms of spin. When you guys learn in chemistry, you always have electrons, they like to be in pairs. You have a spin one direction and a spin the other direction. So if you have the electron that spins one direction, it may be a spin in this way. Well, what we're going to find out is when you have a moving charge, which is a spin, even though we don't know what spin really means, we know it's doing something, and we know it's opposite of its pair. So we think of that as some kind of a motion. And if you have an electron that's spinning, well, what happens if you have a charge that's spinning? We're going to learn with some right-hand rules. That means there's going to be a north pole pointed up onto that thing. And then if you have an opposite pair that has the other spin on it, that means it's a spin like this. That means that the north pole is down on the charge. So one electron has a north pole up. The other pair has the opposite spin or a north pole down. You add those two magnetic fields together and they cancel. So hence most things you really can't turn into a magnet. Even a lot of metals you can't turn into a magnet because they have the perfect pair between one electron and another one. So they're going to show no magnetism whatsoever. So popular magnetic materials are, they're not rare earth ones anyway, or at least the iron, nickel, and your cobalt. So you may have learned this in your chemistry class that iron, nickel, and cobalt are a little different in their pairing. You would think that for every one spin in one direction, you'd have a spin in the other direction as well. Well, iron, cobalt, and nickel are a little different. Their pairing is a little strange in that you have like maybe up to 5 or so. They're all in one direction on every atom. That means on that iron atom, you might have 5 unpaired per atom. They're all pointing the same direction. So if you have 5 unpaired electrons in that iron atom, that means you have 5 of these that are pointing the same direction. That turns that whole atom of iron into a polar atom. You have a definite north and a south side. So what happens to make iron into a magnet, what you want to do is you want to line up all of those atoms. So they're all the unshared pairs in the atom. So you're lining up the atoms all in the same direction. So I have an iron skillet, and that iron skillet, it's not a magnet. However, you can stick a magnet to it pretty easily because what that magnet does, when you get that magnet near the iron skillet, it rearranges those atoms, those iron atoms within the iron skillet, and it makes them point in the same direction as the field. And so it turns that iron skillet into a magnet. I take the magnet away and it's not a magnet anymore. So what you can do, I could turn my iron skillet into a magnet. I could just put it in a very large magnetic field. If I want it to be more permanent, I would take that iron skillet, get it really friggin' hot, pretty much almost to melting. But if I melt it, it's not a pan anymore. But I get it almost hot to melting, then I put that pan in a strong magnetic field, and I cool that pan down in the magnetic field. Now I've got a permanently magnetized iron skillet at home. And that's exactly what happens with the Earth. So let's go back to the Earth picture a little bit. So what happens on the Earth, there it is, as new crust is made. Whoops, that's a little too far. As new crust is made, this molten crust, well, the iron in that new crust lines up with the pole in the Earth. So they're all in one direction. But as we study some of the newer crusts getting to old, we've noticed in some of the old, the poles are all flipped. So the brand new stuff that's been made is all pointing, the fields are all pointing in one direction. But you go several thousand years earlier in time, and we find rocks on the seabed that are exactly in the opposite direction, because that's where we're making a lot of new crust right now, is underneath the water. Where there's some plates that we're making brand new stuff. And as you go across those plates, you find out it goes north, south, north, south. They actually flip. So every so often, we know the magnetic field of the Earth has flipped, because we have a record of that in terms of the crust. The magnetic plates, they're actually magnetized because they cool down in that magnetic field, so they're a permanent magnet. But they've flipped over time. So the big question is, yes, the poles of the Earth do flip, but when they flip, what happens to this field externally? Does it disappear? And if it disappears, for how long? Does the flipping happen in seconds, microseconds, years, century? How long does it take? Because the danger is, if this takes a very long time for this to flip, the danger is that we're without this protective magnetic field. And we're about to learn that when we have charged particles that stream like crazy from the sun, they hit that magnetic field. One charge goes one direction, the other charge goes the other direction against the field. And that's why you have the Aurora Borealis north and the Aurora Australis, I believe, at the southern hemisphere. So that's how you can have a permanent magnet within a bar magnet. Okay, so let's go clear back to this slide over here. So what happens is, the way you can make a bar magnet is you get these to line up all in the same direction. You can actually you could even magnetize a pin. Had we been in class, we would have taken a bar magnet and a little stick pin that you would use for sewing, and you just go like this in the same direction along the bar magnet, and it actually magnetizes that little pin that has iron in there. And bar magnets, if you jolt them, if you drop them a lot, they tend to lose that magnetism, because now these atoms are starting to vibrate and they go in different directions, and you have to put them in a remagnetizer, which is a strong magnetic field that relines up all of that stuff. But my point is, the only way you get a magnetic field, you actually have to have a moving charge. If you don't have a moving charge, we don't have a magnetic field. We're going to get a little deeper into that at a later time. Alrighty, so here's the goods on the forces and everything. Okay, so to find the force exerted on a charged particle that moves at some velocity through a magnetic field. Okay, it's going to be our first right-hand rule that we're going to learn. Okay, let me pause for just a moment. All right. What we're looking at is, anytime you have a charge moving in a magnetic field, there's going to be a force on it. Now, this is our first right-hand rule. It's going to be a little tricky. So everybody has, well, at least everybody in class still has a right hand, so it's going to be pretty useful for you. So the way we use this right hand is to find the direction of forces on a moving charged particle in an external magnetic field. So first of all, the thumb we're going to use to represent the speed. There's more than one kind of right-hand rule, but we're going to use the right-hand rule that uses for a charge in an external magnetic field. Thumb always points in the direction of the velocity of that charged particle. Now, the hands point in the direction of the magnetic field, which always goes from north to south, okay, in the external magnetic field. And then the palm of the hand represents the direction of the force. So in the diagram, that force is actually coming out of the page. Okay, the charged particle is moving upward, the field is to the left. That means the force is coming right out of the page. Now you might say, hey, Mr. Olson, what if this was an electron? What would be true if it's an electron? That's an opposite charge. Well, that means you use your opposite hand. So you'd use your left hand, or use the back hand as being the opposite direction of the force. So for a charged particle, like being a negatively charged, if that was going up through the field, I'm going to use my left hand rule, because it's the opposite hand, the opposite field. The velocity is upward, the field is still in the same direction. Now the force is into the page, or into the computer screen. So it's in the third direction. So the point is, this is actually a cross product we have between the V and the B. This is not the vector part. The vector is with the velocity and the field. So we're going to take a pause there and come back in just a second as the time runs out here for us.